Properties of solutions, the characteristics of solutions falls into a category of what we call colligative properties. So let's just take two substances, typically a solute like sodium chloride. You know, it dissociates in water to Na plus and Cl minus. And then over here, let's have a beaker of good old H2O. Now, H2O has its own unique boiling point and freezing point. It's got vapor pressure. It's got a thing we'll explore called osmotic pressure, and those are unique to H2O. Well, sodium chloride also has that set of properties, but they are very different properties because it's a different type of substance than water. Now, here's the deal. If I take the sodium chloride and I put it into the water and it all dissolves into sodium cation and chloride anion, I'm going to have a solution, and that solution will have a different set of properties than either the pure water or the sodium chloride. It has a collective set of properties, and we got a fancy word for collective. We call it colligative. All right, so that's what we're talking about when we talk about colligative properties. We're just talking about the collective properties, the combination of solute and solvent. Colligative properties, some strange effects in nature. Salt will cause ice to melt even below temperatures of 0 degrees Celsius. So the temperature at which the solution melts will be lower than pure water. Sugar will do exactly the same thing, not as effective as a salt will. Some salts are more effective than others. Calcium chloride, for instance, works better than sodium chloride. And salts also prevent water from boiling at the normal boiling temperature for water at 1 atmosphere of pressure, which is 100 degrees Celsius, and it tends to elevate the temperature at which the solution will boil. Sodium chloride will dissociate into 2 particles. So every time 1 mole of sodium chloride dissociates, you get 2 moles of particles. And that's just a mole of sodium cation and a mole of chloride anion. 1 plus 1 is 2. However, if I take calcium chloride down here and I dissociate that in water, and it is a soluble salt, I wind up with, for every 1 mole of calcium chloride, I get 1 mole of calcium ion and 2 moles of chloride ion, or 3 moles of particles. And the way that it turns out is that it's not really the specific identity of the solute which will change the characteristics or properties of the solution the most. It's the number of particles. So the greater the number of particles, the greater or the more extensive that the boiling point will be elevated, the freezing point will be depressed, the vapor pressure will be depressed, and the osmotic pressure will be increased. And we'll get to those. Okay? So it's really about the number of particles. So if I look at molecular compounds like sugar, they don't dissociate into multiple numbers of particles. They definitely dissolve. But when they dissolve, if I have a mole of sugar, I will have a mole of particles. So when we're looking at molecular compounds, we're looking at a 1 mole for 1 mole ratio of particles. The practical use of colligative properties, well, de-icing roads with salt. And calcium chloride, definitely a practical use if you're from the north, where it snows a lot and the roads ice up and become dangerous. You want to lower the temperature at which the water freezes, and so you'll sprinkle on the roads either sodium chloride, or even more effective will be the calcium chloride because you get more particles per mole. Antifreeze is used in radiators, and it raises the boiling point and lowers the freezing point of the water that's in your radiator. Hypo and hypertonic solutions, we'll take a look at that with respect to osmosis. Preserving by salting and candying foods. There's not much that I'm going to be able to tell you about that other than salting. When I was in the military, we made a lot of jerky in survival situations, survival school principally, and we used salting of meats, and then we would dry those meats, and that salting would keep them from rotting. It was just an unfavorable medium for bacteria to get in there and cause the meat to rot. Candying foods, I know absolutely nothing about candying foods. Okay, let's talk about the effect of osmosis on cells. And if you're a biologist, the term of osmosis is very familiar to you, and it's simply the passage of very, very small molecules. In this case, this is going to be water through a cell membrane, which is semi-permeable. And depending on whether the external solution is hypertonic, isotonic, or hypotonic with respect to the cell, will determine which way water will pass through that cellular membrane. If I have a hypertonic solution, that means my concentration outside of the cell is very high relative to the concentration of solutes, and we're just going to say salt as a dissolved solute inside of the cell. So the cell concentration inside is low relative to the concentration outside the cell. So that would be consistent with, let's say, consuming excessive amounts of salt in your diet. Why sailors who are cast adrift on the sea, if they drink salt water, what happens is that water will pass out of the cell to the external environment, and what that water is trying to do is equalize the concentration of the salts inside and outside the cell. This is called crenation, when the cells literally collapse because they lose all of their water content. But that's what osmosis is doing. It's trying to equalize concentration inside and outside the cell. And so what winds up happening is you have massive amounts of dehydration. Okay? And sailors who are drinking the salt water because that's the only water they have, they want to wet their whistle, they want to hydrate, they wind up dehydrating, brain cells, neurons malfunction, they hallucinate, and eventually it will kill them. If you have an isotonic solution, that's sort of the Goldilocks zone. The concentration outside the cell and inside the cell are equal to each other. And if they are equal to each other, you have water passing into the cell at the same rate as water is passing outside the cell through that semi-permeable cell membrane. And everything is just fine. And so that's an isotonic solution where you have equal concentrations inside and outside. Now, you wouldn't think that you could drink too much water, but you can. If you drink excessive amounts of water, and that's really very difficult to do. I have heard of it being done as a stunt before. Very, very bad idea to drink water excessively, because now you have a very low concentration of salt outside the cell, and what happens is water will move inside the cell at a much higher rate than water moves outside the cell, again to try and equalize that concentration. And that can be very dangerous. You can have cells, and the depiction here is of red blood cells. You can have cells swell and eventually burst, exceeding the tensile strength of the cell membrane, and that can also be deadly. So ideally, you want an isotonic environment external to the cell, not a hypotonic or low concentration of salt outside the cell, and not a hypertonic, high concentration of salts outside the cell. Colligative properties. Colligative means collective. Collective properties don't depend on the identity of the solute, only on the number of solute particles. That's what we look at. If it's a molecular solute, they form 1 mole of molecules for each mole of dissolved substance. Molecules don't dissociate. So it's a 1-for-1. Sugar and ethanol and any molecular compound, it's a 1-for-1 ratio. Ionic solutes dissociate based on their formulas and the number of ions to form the number of moles of particles of the substance dissolved, and we're going to go over that. So ionic solutes dissociate, so they'll always form more than 1 mole of particles per mole of substance dissolved if they dissolve. Ionic compounds dissociate. So take a look here. We have sodium chloride, and here we have 1 mole of each substance. For sodium chloride, you get 2 moles of ions, sodium cation and chloride anion. For calcium chloride, you get 3 moles of ions. This is ideally. You get 1 calcium and 2 chloride ions. This is not diatomic chlorine. Hopefully you know that by now. This is ammonium nitrate. This actually dissociates into 2 moles of ions, guys. So that's going to be the ammonium cation with a +1 charge and the nitrate polyatomic anion. So that's 2 moles of ions. Okay, and then here is sodium phosphate. You have 3 moles of sodium cation, 1 mole of phosphate, so that gives you 4 moles of ions. So we'll practice at this a little bit. And we're just dissociating compounds. So for instance, if I have a 0.25 moles of calcium sulfate dissolved in water, here's calcium sulfate, and I put it in water, H2O, will assume complete dissociation into calcium 2+, that'll be an aqueous solution, and a sulfate polyatomic anion in aqueous solution. The big mistake here is people want to break up the sulfur and the oxygen. That's not the way it works. This is sulfate, a polyatomic anion. If this is 0.25 moles, then what you get is 0.25 moles of calcium ion and 0.25 moles of sulfate. 0.25 plus 0.25 gives you 0.5 moles of particles. The particles being ions. Okay, that's the way it works.